Hi, everyone. Welcome to this new season of Additive Talks. If you are joining us for the first time, please know that Additive Talks are a series of panels that focus on discussing the use of additive manufacturing technologies in a given industries. No pitches, just lessons, mistakes made throughout the adoption curve, and new opportunities. If you have been here before, thank you for listening to our Inside Additive Manufacturing. Well, without further ado, I would like to give the floor to our experts so that they can introduce themselves as well as the company they represent. Melissa, can you go first?
Yes, most definitely. Hi, thank you, for having me again. I really like this forum and appreciate being invited. So my name is Melissa Orm, and I'm Vice President at Boeing, leading additive manufacturing across all three business units of commercial airplanes, Boeing Defense and Space Systems, and Global Services, and also lead research activities that are aimed at additive manufacturing in terms of materials development, technology development, really focusing also on our innovative designs in the business units that solve complicated engineering problems and add value to our products, qualification, certification, and the digital thread of everything that we do, so that we can continuously improve and make our products and our production better. That's a little bit about me now at Boeing.
Thanks, Melissa. What about you, Bill?
Good morning, Teddy. Thank you very much. So first of all, I'd like to express my appreciation to 3D Adept Media for the invitation to be here today. So thank you to them, and thank you to everyone who's participating. So my name is Bill Haddad, and I have the pleasure of leading additive design and manufacturing at Collins Aerospace. Collins is one of three business units and is involved in the RTX Corporation alongside of Raytheon and Pratt & Whitney. And here at Collins, my group is at the enterprise or central level, where we work quite closely with our 6 business units, our 6 internal customers, and I'll explain more about that later. But really leading the adoption and driving additive strategies across the entire enterprise of Collins Aerospace. So much like some of the functions that Melissa talked about, we get involved with all aspects of the AM value stream, to include looking at design tools, engineering tools that our design engineers, that our engineering workforce would apply, all the way through the industrialization process, to include I have responsibilities for 2 production sites, as well as understanding suppliers and supply chain in the additive space. So again, a great pleasure of mine to be here this morning. I look forward to our conversation.
Thank you very much, Bill. Short reminder for the audience, please, if you have any questions, make sure you write them in the Q&A chat in front of you. We'll publish them, and we'll make a pause at some point during the conversation so that Melissa and Bill can answer them. And now, before we dive into the heart of the conversation, I would like to understand the positioning of Boeing and Collins with regards to additive manufacturing, respectively. I will start with Melissa. Boeing has been using AM for so many years now, yet the company has built a reputation on a very traditional technological expertise. What are the key milestones that have marked the company's adoption of AM over the years? Or let's say, how do experts at Boeing, perceive additive manufacturing?
Well, so the question, that Boeing takes a traditional approach, I think that's probably true. We don't have the philosophy of failing fast and fail often, as many of the startups do. We really have the mindset of, intelligently iterating, right, and building a solid foundation, because everything that we do has to really demonstrate repeatable and reliable performance. Everything is built on that foundation, right? And so we're basically, creating these large databases. They're coupled with modeling and simulation, so that we feel confident, we understand the machine's behavior, we understand their stability, and that, we can really guarantee the foundation of a stable process. With respect to sort of timeline, if you'll allow me to share a chart, because I have a timeline. So let's just see if I can do this without, breaking the system. And hopefully I can do that. Share, I'll share the screen. Okay. And okay, so hopefully I'm sharing that screen. This is like our timeline
Yes.
of metal Boeing additive manufacturing. And you can see it really began in 2011. And we've been working very methodically throughout the past, 24 years. You'll see in the beginning with some one-offs and some demonstrator parts, but really beginning in about 2016, 17, we've just accelerated. And there's a lot of things that we've done that are not on this chart because they haven't been cleared for public release, but we've been really growing exponentially in the past 3 or 4 years in the space of satellites, drones, autonomous vehicles, fighter airplanes, and helicopters. And then at the end of this year, we'll have our first powder bed fusion part on a commercial airplane. And that's taken a long time. And it's really because, first of all, with the FAA, it's a harder certification process than a satellite, right? Because there's people involved, and so that's the right, it's certainly correct, and I agree with that. But we just have to have the data, the validation in a much more arduous way with the FAA's basically partnership and collaboration with us. So in terms of milestones, I think you could say that we've been really working, slowly and steadily, and now we have really pivoted. And if you, just very quickly, in terms of polymers, we started even a decade earlier, back in 1990, right? So Boeing does have a 3 decades of experience in additive. And right now, we've recently counted that we have about 140,000 parts flying right now on Boeing products, and these are, a lot of them are polymer, and a lot of them are on commercial airplanes. And if you've flown, you've all been on an airplane likely that has Boeing additive parts on it. It's just not really well publicized. Something that I'm trying to do right here. So anyway, that's a little bit about Boeing's approach. It's really been a methodical and intelligent iterations of how we can demonstrate a repeatable and reliable process.
Okay, good. Well, Bill, you mentioned, thank you very much, Melissa. Bill, you mentioned at the beginning that Collins Aerospace has 6 different, strategic business units related to different, aircraft systems. What's the area that benefits the most from additive manufacturing?
Yeah, that's a great question, Teddy. And so let me first start by sort of trying to describe, if you're not familiar with Collins Aerospace and those 6 SBUs, let me kind of describe kind of the variety there. So as a company, we have broken down into 6 strategic business units that do focus on specific technologies or specific customer sets. And obviously, at a company the size of Collins, given that breadth of product portfolio, it is very difficult to sort of take a one-size-fits-all approach to anything we do, but most notably, in my world, we certainly can't do that with additive. But one of the things we have found out is we're kind of looking at additive from a couple of different perspectives, and we feel those perspectives fit well across that vast product portfolio. The first thing we look at is, current product. So are we able to utilize additive in the production of current products? The second perspective, which is obviously something that we're looking forward on, is new product introduction. And so those 2 opportunity sets have us bring additive to bear in very different ways. And I see Melissa nodding because I think it's very much, agreed upon, across the additive industry. In general, we look at complexity of part as one way that additive can help solve some of the current technologies, right? So if we're looking at current products, traditional manufacturing does struggle in some aspects to produce very, very complex parts. And that's one of the areas where additive does an amazing job of overcoming that complexity. If you think about, larger parts with many internal channels, many passageways, things like that, significant geometric challenges. If you think about something like traditional machining, a little bit of a challenge for some of those applications, a lathe or a turn machine or something like that. So part complexity is one way we sort of categorize or we look at parts as we look at candidate parts, with respect to the current portfolio. Going forward, with respect to new product introduction, we don't have some of those current geometries. We don't have some of those current size restrictions. And so additive will have a completely new design space. We talk about sort of clean sheet design where all of the benefits of additive can be applied. And we're really excited about those opportunities. There are some of them now, but we believe that there are many more to come in the future. And that's where we believe additive will truly show its full breadth of capabilities. And we'll be able to really apply the talents of our workforce and really drive solutions for our customers. So we're excited about the future, while certainly focused very much on the present. And like I said, how additive can overcome some of the current manufacturing challenges.
Yeah. Well, thanks, Big. I would like us to discuss a little bit applications driving industrialization here. First, AM design techniques and design strategies for aircrafts are being adopted differently in sectors like, civil aviation, space, and ultralight aircraft vehicles. Some parts can be produced via AM with existing designs, while others might need a completely new design, which is an investment in the long run. It will require additional efforts to be accepted as a flying part. So maybe Melissa, you can go here. What should we prioritize in such cases? What's the ideal design approach or technique we should, have when looking to produce with additive manufacturing?
Thanks for this question. It's a really good one, and it really echoes a lot of what Bill just said. Because the first part of the question, whether or not a part can just be produced, with additive manufacturing, and others need to be redesigned. I assert that basically, if it doesn't need to be redesigned, or you choose not to redesign it, and you're just swapping out additive manufacturing for traditional manufacturing, you're not going to add any value. And you're unless you're addressing supply chain shortages, right? So there may be times that you want to print the part to get it fast, and then speed might be your value driver. But the same design won't unlock any benefits of additive manufacturing, and it won't enhance the performance of your vehicle. So at Boeing, we use additive manufacturing not just to say we're printing a part, or we can print it. I always say, but should you, right? Why would you? And the why is very important, and there should be a good answer to the why, right? And so it's not just another way to make a part. People say additive manufacturing is just another tool in the toolbox. I'm not so sure about that. I mean, it is, but it's a way to make better parts, not just the same part. So I look at ways of making parts that can't be made with traditional means, right? This means that parts they have been optimized and they have been lightweighted. Maybe they have embedded cooling channels within them, or maybe we've consolidated, tens or hundreds of parts into one, right? And this is where the value then is added to the actual vehicle, right? Because we're trying to enhance the value to the vehicle, not just make an additive part. Right? Adding additive parts doesn't make a vehicle better unless they're lighter in weight, unless they're smaller, unless they're given more functionality. Part for part swaps, if they can be manufactured traditionally, I always say they should be manufactured traditionally, right? And so what you really use additive for is those designs that add value to the end component. In the Boeing's case, it would be, airplanes or helicopters or satellites. You always look, what's the value driver? Part for parts won't have one. So it's always in a redesign, unless you can't get the part and you need it fast, like there's a supply chain shortage on a certain cast or something like that. And then you'll just, try to figure out how to make that additively and certify that.
Yeah. Well, I should have probably started with this question, maybe regarding the different fields of activity that the space industry covers, because there are so many, different, let's say, segments in the space industry. Bill, what are some of the space applications where additive manufacturing offers a better way to manufacture compared to traditional manufacturing techniques?
Yeah, so I'm going to follow up on what Melissa said. I think it's absolutely critical that we talk about improving the performance of a part, right? So again, like Melissa said, not just making a part additively because. And so at Collins Aerospace, we follow almost identically some of the things that Melissa just mentioned. One of the questions I will always ask my customers, again, the 6 business units of Collins that we spoke about earlier, I'll always ask them, what problem are you trying to solve? And if it's a performance problem, great. And even if it's, as Melissa pointed out, if it's just a supply chain problem, quote unquote, that's a problem that we can help solve. But it always starts with that. What is the problem you're trying to solve? In the case of a space application, again, all of those questions still apply. But one of the really key areas of space that we all think about is the weight, right? The first problem of putting something in space, whether it's a satellite, to Melissa's point, or it's a manned vehicle, a deep exploration satellite, anything like that, the Hubble telescope, any of those different applications, is the weight. Overcoming the gravitational pull of the Earth is probably the fundamental problem, or the first problem, as you look at the performance of a vehicle. Obviously, as we all know, additive has a great advantage over traditional to lowering the weight of a part. And so therefore, as you start to string together parts, become systems, become larger systems on a vehicle, that is one of the ways that additive can certainly apply its benefits to the space industry. And so again, I think that's a really unique or interesting area that as we continue to go forward, the additive industry, continues to go forward, working with the space industry. I think there'll be great advantages of that. There are different studies that talk about the cost of a launch. And I think that if we can really change the economics of how the space industry values a launch, how it prices a launch, I think, again, it opens up even more opportunities for our space customers. So we're really excited about that.
Thanks, Bill. Well, I feel like my next question from Melissa, well, it's a little bit similar to something I've asked earlier, but Melissa told me, unconsciously, I feel like the industry seems to define a production part as the ideal good, AM application. What are your thoughts on this? Would you say that AM delivers the most added value in such part?
So this is a good question, and my Boeing team hears me say the same thing over and over. What our mission is at Boeing, and that is, our mission is to add value to Boeing through additive manufacturing. That's all. Add value to Boeing, and how do we do that? And there are a lot of different ways to do that. One is to accelerate new product design, and we do that with making prototypes, making tools, making machine fixtures, right? Another could be making wind tunnel models. So we do a lot of things like that help our production, development. We make tools in our factories that are more ergonomic, so that our factory workers don't have to crawl into spaces upside down, and they can do things, more in a more healthy way. And also, value can be added by creating parts that enhance our vehicles, right? And that's what people mostly think of, right? But additive manufacturing is good for all those things, right? I mean, how much importance do you put on helping a worker stay safe? I mean, I put a big importance on that as well, right? But basically, we do like to say that additive manufacturing adds a lot of value when you are enhancing your vehicle. And I don't look at it on a part level, because people have asked me very often at Boeing, Melissa, how many parts are you making? And I'll say, that's the wrong question. I'd like to count the number of parts I'm eliminating, right? Because with additive manufacturing, I can, consolidate many parts into one. I can make it more, the whole component more producible, right? I get a lot of, I eliminate a lot of workmanship, sources of potential problems. I have a whole, issue with logistics. A lot of it goes away. I'm eliminating parts or fasteners, right? And so this is where I'm helping with producibility and with respect to, the actual part. Now, I think your question was more probably on production parts, right? Well, we're doing a lot of work with, I'm slowly getting up there. In terms of Boeing Defense and Space Systems, we have a new product line which is a small sat, and this is in collaboration with Millennium Space, and it's fully 3D printed. And we are have it set up such that we can create many of these a year. And it's the first additive application that's really come back with a positive ROI. In fact, it's 2 orders of magnitude our return on investment. And so it's fully 3D printed, and it's a small set, so it's like 20 by 20 by 20 or 24 or whatever inches, and it's every one that we create, we're actually evolving and getting better, making it lighter weight, so that we're replacing the traditional honeycomb panels with a very innovative additive design. And every when we make it a little bit better, we make them a little bit lighter so we can have more payload. And these are really good applications for additive because each one is customized, right? It's kind of it is a small lot production. The whole satellite has many pieces, right? It has 6 sides. It has stuff going on in the middle. But we make a finite number a year, but each one is a little different, right? And that's why it's a really good application for additive manufacturing. And everyone's looking for the killer app like the LEAP fuel nozzle, right? The GE engine, and that's okay for one part. But what we're doing right now in space and defense, instead of making one part 100,000 times, we are making 1,000 parts 100 times. So we have a lot of smaller production lots, but many unique designs that are all on products. They're all certified from the regulator. So basically, there's satellites is a really big application space. And we're just now getting into other space and other parts for fighter aircraft, F-18, the Chinook, and then some autonomous drones as well. And as of course I said, the civil air is different. But what we've talked about with Bill is that what we're doing right now is part swap outs for existing parts. They don't really add a lot of value. But we are doing that because we need to, create that relationship with the FAA, understand how you certify, and with the FAA, a part that has a significant manufacturing change, right? And so, we do that. And what we're really, intending to use additive for on commercial airplanes is what Bill alluded to as the clean sheet approach, where you can really then design your actuators so they're smaller, so your wings are thinner, so you have a higher performing aircraft that has less drag and is more sustainable and things like that. So it's really for, in airplanes, so you get your benefit in new designs.
Well, thanks. I think that we have a couple of questions that maybe need to be answered right now. And before, reading the questions, I would like to start with a remark from James, who said, additive manufacturing is more of a designer's strategy than a material process. This is important. The AM process refers to the mechanics of producing a part, but the real goal is to make the part better. I've always thought this way. Thanks, James. I guess the speakers agree with you on this one, on this remark. If you don't, feel free to say so. And the very first question James asked is, do you offer which technologies you're working with? I heard power-based, but is it with laser, maybe, or only using FDM or polymers? James, if you can just, specify for which speakers you're asking this question. Is it for Boeing or Collins Aerospace?
We could probably both answer. I don't mind answering, and probably, Bill can answer. So in terms of what we're working with right now, for me, it's, the same mantra, whatever adds value to Boeing, right? And currently we're spending a lot of time with laser powder bed fusion. And are also working on, we also have certified electron beam powder bed fusion. Some of those parts on that timeline were made electron beam powder bed fusion. We're maturing DED, directed energy deposition, powder-based as well as wire-based. We have, since 2017, qualified parts through a supplier with wire-based directed energy deposition for the 787. We have about 7 different part numbers on every airplane since 2017. We're using, in terms of polymers, we do use basically probably every technology you can think of here at Boeing. Well, except for maybe some of the new niche ones. We don't use binder jet simply because we cannot get the density that's required for aerospace grade products. And we're continuously evaluating and maturing any technology that will have application on any of our products. So we're very open-minded, not just set on one technology, right? We're exploring kind of anything that helps us.
All right. What about you, Bill? What technologies are you using at Collins?
Sure. So very good question, James. Thank you. Very similar to what Boeing is doing, right? So certainly, a lot of our focus is on laser powder bed. I think that's probably a very common approach across the additive industry. We do also have a lot of experience both internal and with the supply chain on other forms, DED, EBAM. I'm trying to think of all the different categories. I know there's 7. We do have internal capability for non-metallics. I call them polymers. We have both internal and external experience with that. We're actually working with a smaller company to help them develop their next platform. So we don't want to be machine manufacturers of additive machines, but where we can give some guidance, we can work with some early stage companies. We have taken that approach as well. And so, yeah, like Boeing, we're working across the spectrum of all of the different AM methodologies. And much like Melissa said, we believe that there's application for each. And so when we look at a problem statement, when we look at what is the problem we're trying to solve, again, going back to an earlier comment that I made, we recognize that the different methodologies will have advantages and disadvantages. And so we like to select the proper technology for the right application. I think that, again, as we continue to expand our internal capacity, it will be primarily in powder bed because that's where the majority of our experience is. But again, we are, like I said, we are not opposed to bringing in new technologies, and we do have some of those already in-house.
Okay, good. Next question is from Steve. Do you have a specific in-house process to assess the manufacturing readiness level of a given technology for AM applications?
I'll start on that. The answer is yes.
Okay.
We have a very arduous process to assess the MRL, manufacturing readiness level, and technology readiness level. It goes through a Boeing gated process. There are a lot of stakeholders involved. We have a whole organization called BR&T, Boeing Research and Technology, that set up this gated process where you have to make sure you deliver the certain number of artifacts, you demonstrate the right criteria to be advanced to a certain level. And for example, we might say we have a certain level right now at TRL3, and we're trying to get it to TRL6. We'll start putting it on vehicles in a one-off fashion around 6, and at 9 or 10 it's fully just ready to go, right? So we do have it's internal, and everything that we do aligns to that.
Okay. What about you, Bill? What does it look like at Collins?
I feel like, and for good reason, everything I'm saying is like, yeah, I agree with Melissa, right? Because our industry is so
it's the same
industry, right? And so we do have the same standards. So absolutely, we've got the TRL MRL process, same as Melissa, very, very, very regimented through the different gates, and it requires sort of like a non-advocate review board to approve any of our technologies moving from the current gate to the next gate. So again, like I think Melissa used the word arduous, right? A very arduous process, right? Very, very difficult to move forward, right? And for good reason. We've also, and I was going to touch on this on an upcoming question, but I'll briefly mention it now. We are looking at something that's coming out of the FDA regulated industry, whether it be medical device or pharmaceuticals. It's called what we've called it now, the QQ plus, right? IQ, OQ, PQ, MQ. And so that process of helping us focus specifically on our machines and the output of the machines with respect to additive manufacturing is another process that we are familiarizing ourselves. We're starting to put some specifics around how RTX wants to approach this. Again, for a specific application in the additive manufacturing space. The TRL MRL process that I mentioned really goes across anything that we do at Collins, any technology that we do at Collins, specifically this QQ plus we're trying to adopt for additive. So, and they do work hand in glove. As you move through the different TRL gates, the IQ process, the QQ plus process, if you will, also sort of takes root there, right? So it's a little bit of a matrix, but aligning those two processes, making sure that we cover all the necessary requirements, the necessary steps to comply with the requirements that we've set forth is something, again, that we're truly trying to focus on right now in the additive space.
Okay. Well, thanks, Bill. Next question, the third one is from Eliezer about data. Data have always been one big challenge for AM users, as they are crucial to ensure predictability, stability, and quality control. Taking the example of one application, how do you address this challenge? That's a question. I feel I feel like this is a Melissa.
I like this question, and because somebody asked me in a different forum, what is 2024 the year of in terms of additive, and I said data.
You said data.
And I really believe that we've had the years of getting like faster machines, more lasers, blah blah blah, and this is the year we're of data. We're more mature now, and so what Boeing has done is that we're taking our end-to-end value stream. As we all know, printing is like a tenth or less of everything that has to happen when you make a part, right? And so we're taking the data from every aspect of the value stream, from even before printing, the simulations, your CAD, all that, and then we're folding that into our digital thread, and that's not easy to do because the data is locked in all these different sensors, and they don't speak to each other, right? And so it's quite hard to contextualize your data, archive your data in a way that's accessible for your data scientists now to create their machine learning algorithms that are going to use that data to continuously improve. And I used to say optimize, but now I say continuously improve, because optimize sounds like an end state, but we're continuously, getting better. So we're creating that digital thread. I'm quite proud of my team. We've created a team, we call them the Intelligence Center. They've managed to, create ways to extract data automatically from the machine, a printing machine, but then also like our heat treat ovens, our, the post-processing, and then to standardize that in such a way and to add context so we know what the data represents, right? So you're not creating models, that are misrepresenting things. And then, so we have this in our data archive library. It resides on the cloud, and we're able to now create predictive quality models, right? And so for me, this is really important because it helps us understand, what has happened, why it happened, it won't happen again, and what we should do about it. Right, and those are this is what the data tells us. So it's really important that we have access to the data, and we contextualize it, right? Because you really need to understand. You have to use the right data, right? And we have to make it accessible for our engineers and data scientists to use it. A little statistic: in industry, it's kind of known that data scientists spend 80% of their time formatting or searching or cleaning their data. and 20% of the time doing their cool stuff, making their machine learning models. And so, that's one of the problems, I think, because if you look at each of these just machines, for example, they all have different sensors. They'll have different formats. They'll have some machine makers don't let you have the data. Some of them do, and it's all about really having open access to as much data that you can to add that context so that you can create your models for continuous improvements. It's probably a little long-winded answer, but I really like the data aspect. So thank you for asking that question, Alicia.
I'm curious to hear if, at Collins, they have a different approach.
Well, I'm gonna repeat myself. Not really a different approach, right? But if you think about, there's a term that we're all familiar with, right? Industry 4.0, and at least for here at Collins Aerospace, additive is truly the first I4.0 manufacturing process, right? That we're bringing into the company. We're trying to take other legacy manufacturing processes and improve them, right? Start to digitize them, et cetera. But if you think about additive, it is truly the first Industry 4.0 manufacturing process. And so, like Melissa mentioned, printing is only one step. So we've defined the value stream of additive in 14 different steps. And so printing is step 4. But at every one of the other 13 steps, there is an opportunity to generate and capture that data. And as Melissa said, one of the things we're really focused on is how do we not only capture the data, right? Storing data is easy, right? Melissa said, right? Like, unfortunately, data processors, data engineers spend way too much time, cleaning the data, massaging the data. So how do we capture the data efficiently and effectively? And then most importantly, how do we utilize the data for that continuous improvement that Melissa mentioned? And it is an area that we spend probably far too much time on, but it is necessary. It is critical to the success, not only of the parts and the products, but it's critical to that continuous improvement that Melissa mentioned. And so, yeah, like Boeing, we're spending a lot of time on that. But we have to embrace that, right? Because we have data now that we never had before, right? At every step of that process, every step in that 14-step process. And so we embrace that rather than see it as a challenge, because it does give us the opportunity for that continuous improvement. How do we do better tomorrow what we did today? And we, like I said, at Collins, we really embrace that opportunity. It's not easy, right? But that's okay, right? It's worth it because we've got the opportunity, again, to always do better tomorrow than what we did today. And so it's going to be a challenge across the entire industry, right? Because we certainly understand the volumes of data that are being generated, but truly finding what's of value, right? Of all of the terabytes of data that are being generated on sort of an hourly, daily basis, what are the true nuggets, right? What's the true value of that data? What are those key specific KPIs that we need to focus in on, again, so that we can feed them back upstream in the process and undergo process improvement. In some of our facilities that we have, some of our additive facilities, we're looking at how do we link the lab, right? So we have in-house laboratory capabilities. How do we link those data generation centers straight into the production center? So can we see in almost real time, not quite yet real time, but in almost real time, can we see output, feed that back to our engineers and back into the production center as soon as possible in order to correct? Not in a specific build, right? We're not there yet. We're not correcting in a specific build, but how do we correct almost real time that next build, some of the output that's gone through the lab and now can be improved in the production center? So again, it's speeding up some of those turn times, right? Speeding up what would typically take much, much longer to analyze the data and find the applicable nuggets, like I say, that helps improve that next build. So the speed at which we can do that will certainly define some of our success in that improvement cycle. But again, we embrace that challenge because we're so lucky to have more data today than we've ever had at any point in our manufacturing past.
Well, that's the first time I hear something like that people are really lucky and happy to have data today more than ever before. Next question is from Mike. Question number 4. What are the unique challenges that you found around making AM scalable and repeatable system to system and site to site, and maybe even month to month? Oh.
I can answer that because there are a lot of challenges, and I don't know how unique they are, but there's so many different levels of challenges. For example, if say we're making one, well, first of all, the one challenge is that the entire value stream, every single process needs to be fixed, not just how you print it, right? But the heat treat, we have to make sure like that every time we do this heat treat, the thermocouple's on the exact same place of that build, right? If we move it, we might get a different reading, right? We have to make sure that the hip is exactly the same, that that the environment within the chamber is the same. So it's really fixed process end to end. That's for making one part. But now say we're using suppliers. Say that we have one part and we have 5 different suppliers making the same part. Well, if we let those suppliers basically decide how it's going to be oriented, the part, well, we'll have 5 different parts. They won't be the same because a different orientation, different support structures, will have a different layer by layer cross section, meaning that there'll be different heat transfer, different phase change attributes, and so have different material science, right? And so while in the end those parts might look the same, they might have the same shape, they won't actually be the same part metallurgically. And so one of the things that we're doing when we work with suppliers to make sure that we have a fixed process all the way down to how it's made is that we're doing that in-house. We're using our machines for innovation. I like to say so we'll take the part that we want to be printed with suppliers, and we will define the best way, in our opinion, how it's manufactured, the support structures, the parameters, and then we encrypt that with a secure print solution that goes directly to the machine, and it can't be altered. It can't be. We do this for reasons of cybersecurity to make sure that it's not vulnerable. That there's no way it can be altered while it's on its path there, but also while it's there, it's not unencrypted by a human. It doesn't get put on anybody's laptop. It gives the machine instructions on how to do it, and you can't reverse engineer that. And so then we can stream that data back from the suppliers and monitor while it's printing. We can then also understand how many times it's printed. If they've had a failure, we like to know. Sometimes suppliers don't say. They may have built it 5 times, and that would be an unstable process, right? If a supplier just says the one time it works, but 10 times it didn't tell us, right? So it's all about stable process, keeping things fixed, right, in terms of scaling. Now, in terms of machine-to-machine variability, there is machine variability. For those of you who work hands-on, you'll know that even within the same brand and same model, you'll have variations. So when we qualify suppliers, we make sure that we'll do test qualification builds to make sure that we're getting the like data, and we'll have them print many different runs with different powder lots and so forth to make sure that there's no variability, right? And if there is variability, we'll try to help them fix their process. And if it's very off from ours, we'll try to help them, change the flow or other aspects that might be causing change. And finally, the last thing that we're doing, which I think is really important, is we're working on machine equivalency. And this will allow us to leverage data from the older machines that we have a lot of information on for new machines. And so we're working on so that you don't have to start over every time there's a brand new machine that's available, right? Because we want to be able to take the latest, fastest, biggest, most laser, and not be stuck with an older, maybe obsolete machine simply because we have a whole bunch of heritage data on it. So we're working on a program to define what is statistical significance, which allows us to qualify and show that this is in family, and so that we can leverage those databases. And that will really allow us then to scale across many different types of machines, as well as the same machine. So it's all about fixed process, reducing any variability, and in any part of the value chain, from the suppliers, from your own value chain, from machine to machine. challenges.
Well, Bill told me that you have a different system, or well, different approaches to challenges here.
I wouldn't say different approach, right? So I'm not going to spend as much time describing kind of what we're doing, but I think it's really interesting question. So thank you, Mike, for the question. You know, you mentioned unique challenges, and one of the things I think about is additive manufacturing is as much as, if not more, than any other manufacturing process, the most technologically advanced, right? And so it's about the number of variables, right? So the number of variables has increased exponentially. And as we all remember from our basic math classes, right? You increase your variables, you're going to increase the number of different answers that you can get, right? The number of different outcomes. And so like Melissa said, it's really controlling as many of those variables as possible. If you think about manufacturing, if we were moving from machining supplier A to machining supplier B, there would be a number of variables. We've got decades, if not centuries of maturation there that have learned to overcome that variability from manufacturer to manufacturer, from machine to machine. Additive doesn't have that same amount of history, so we're trying to catch up, if you will. But again, we're doing it in two different ways, right? We're doing it with all the different number of variables and all of the different number of machines that are starting to proliferate the market. And that's a wonderful thing, right? Because with innovation, with more competition comes innovation, and we embrace that. We love that. So I think it's really about identifying what are the key variables, what are the ones that will make the most difference, can have the most impact on the outcomes, and controlling those, locking those down in a number of the ways that Melissa said. So again, I think it's about the way you approach identifying those key parameters, those key variables, and overcoming the variability with those as quickly as possible.
All right, thanks. We have a remark from James. I will skip that due to the limited amount of time that we have that remains, and then move to question number 7. Space debris reduction is a big challenge for both space companies and AM technologies, providers. Which 3D printed components of a satellite can contribute to space debris reduction? What other measures can be implemented to mitigate this risk? Well, Melissa, you mentioned at the beginning that Boeing specializes in, had a certain expertise in satellites. I don't know if these questions fall into that spectrum, or we should skip it for maybe later and try to answer it online.
This question doesn't really, question it because it doesn't really apply simply because space debris is like entire satellites that have run their course, right? And so you're not going to pick off parts, in my view, that are additive or not. So I would have to think about that question. Bill, I don't know if you have any comments there.
No, Melissa, I'm not an expert on kind of what currently is contributing to the space debris problem. I know that it is a problem, but because I don't know enough about it, I wouldn't be a good answer here for that question.
No problem. If in the meantime you have key insight that you would like to share into that specific questions, we could always write an article about that later on, so that the audience can be more informed about that. Then let's move to question number 9. Well, not 9. 9 is another comment. Then question number 10. Hi, this is Yash Banda from Fastech Engineering from Virginia. Have you explored wire DD technologies yet? If so, which process are you exploring more, one versus laser wire?
And I think you go first this time. Yeah.
Thank you. Appreciate that. So thanks, Yash, for the question. We're doing both. Okay, and so as I mentioned, right, we're exploring all the different additive manufacturing technologies and applying the best solution for that particular problem statement. So we've got we do have some RAM parts that we've worked with in the supply chain. We actually have a laser wire machine in-house now. So with respect to DED technologies, we're doing both. And again, it's really about what is the right solution for the particular problem that we're trying to address.
And
Okay.
I'll add on to that. Basically, since I think I showed on the timeline, we have this part. There was one part that's a wire DED part that's been in production since 2017 on every 787. So if you're go on a 787, you'll be flying with wire DED parts from Boeing. And there's about 7 different part numbers. They're hefty parts. They're big. I like ED technologies because there's only so much, in my opinion, that you can do with powder bed. And at some point you have to move on to a new technology because the powder handling just becomes really hard. And so we already have matured the wire DED for static applications. And now we're working very hard to refine its microstructure such that it can take fatigue loaded applications. So we're doing that actively at Boeing. And then we're also looking, let's see, it's just wire. We do powder, but the wire, then we're also looking at WAM, right? There's a lot of really nice companies that come out of the UK. Boeing is invested in helping mature some out of Cranfield. And so really, like Bill said, like everybody, it depends on the applications that your company has. And we're exploring everything that can add value, right? Yeah. And Katie, I do like that one statement. If we can answer it, if you'll,
feel free. Do you mean the statement number 8 or number 6? Number 6. Okay.
Well, I haven't read 8 yet. Let's see. Oh.
Yeah. So, statement number 6 from James. Well, you can read it and make a comment. Yeah.
Okay, so it's probably a little bit of controversy, right? He says, I like the statement, AM is a way to make parts better with design changes. The AM process is only a tool to get the part made. Parts need to be made smarter, not faster. Actually, it was his previous statement that said, it's only a way. Here it is, it's statement 5. AM is more of a designer strategy than a material process. Okay, so that statement that I'll not agree with. I won't agree with it for aerospace and defense. For other, commercial products, for other industry, it might be true. But for aerospace and defense, I can have a really cool designed, topologically optimized part, but if it doesn't have the material properties I need, it's useless, right? So I'm always, some people say it's just another manufacturing technology. It's not. You're making a material at the same time as you're making a part, and you can make a material badly, right? If you don't know what you're doing, you could make a material such that it's not going to meet our qualification requirements, and it can't get on an airplane or a helicopter or something like that. So, in my opinion, it's a lot easier just to make a very cool shape than it is to make a really cool shape with the right material properties. So those are intrinsically coupled. And it's if you're doing mock-ups for architecture or something, okay, yeah, maybe that's the case, or other commercial products. But for aerospace and defense, it is absolutely a material process. You're making the material at the same time as making a part, and there are many times when people fail our qualification because they can't meet the material requirements. So I just want to say that. But there's other application spaces where that statement may be correct. So I wanted to say for aerospace and defense, it's not correct.
Mostly right. The ultimate judge of success or not is the part performance, right? Can the part meet the design requirements? Can it meet the performance requirements? And so if a designer comes up with a really unique geometry, but it fails, if it doesn't meet the performance requirements, and ultimately that will be the judge of success or not. So I agree with you that it is not just a designer strategy. I don't necessarily agree with that part of the statement.
Yeah, maybe that's the reason why Martin is saying that, no, James, you are so wrong there. Maybe, comment number 9.
If I can add that James does say in a second one, it's a way to make parts better with design changes, and that is absolutely true. Right?
Yeah.
And I like that statement too, James, that it is a way to make parts better with design changes. And in my view, that's the only reason why you would make you would use additive. You're gonna use the tools of additive that allow you to optimize your part while making sure you're making it with the right material properties that you need, right?
Mm-hmm. Yeah, yeah. We have 5 minutes left. Bill, I don't know if you've answered the questions on wire DD from Yash.
I thought I did.
Okay, good. All right. Sorry, my mistake. My bad.
I'm going to go first there, so I thought I did. I will say, just as a quick follow-up, that like Melissa mentioned, we do have parts that we produce in both technologies that have been qualified. So again, I think it's the DED space is a little less known to us than the laser powder bed space, but we are putting a lot of focus on it. Size of parts will be one of the advantages in the DED space. Obviously, on the laser powder bed machines, the boxes, the build chambers are only so big, and you've got a little bit more size freedom with DED. And some of the subcomponents that we make at Collins do exceed the current geometries of laser powder bed. So we do believe that DED has a lot of application for those larger volume parts at Collins Aerospace.
Okay, good. Thanks. Question number 12 from Marina. In terms of data accessibility, which step in the EM process chain is currently the bottleneck? That's a good question.
The question is, which bottleneck are you referring to? Basically, you know, in terms of data accessibility, it really depends on you know, the machine maker that you have, right? And at Boeing, we used to only work with one, and now we have 3 different machine makers, and they all are different in terms of data accessibility. I don't want to name names, but some are much better than others. And there have been companies that people out there probably know who they are that say, my machine is a black box. It's so awesome. You'll never need to go in and look at the data, and you may not have it. And so that for me is a non-starter, and our company won't go there. So in terms of the data extraction from the printing machines, you know, it depends on your partnership with the machine OEM, your relationship with the machine OEM, basically, and getting that data.
Well, Melissa, if I may add something, from my understanding, this question is like you have different, you know, steps in the manufacturing value chain, like pre-processing, the manufacturing phase itself, then post-processing, and everything that happens after the post-processing. So I feel like maybe the bottleneck in terms of data accessibility will have been around a specific, you know, step that manufacturing value.
Honestly, it's about, with us, it's really about the printing data accessibility, because we are able to take, you know, we have our own individualized sensors on our different post-processing steps, right? So we have sort of our customized, you know, homegrown solutions for our end-to-end value chain, right? So we don't have bottlenecks in data. We have bottlenecks in other things. We have bottlenecks in producibility, I will tell you, but we don't have bottlenecks necessarily in data acquisition. You know, I mean, for example, we get, you know, when we do tensile testing and we need to bring that data over, I wouldn't say that's necessarily a bottleneck. It's just kind of a pain because we get it in an Excel spreadsheet and we have to, you know, convert it, right? But you know, and we have sensors on other downstream, you know, machines that we've been able to extract. And so it's really the sensors from outside companies, right, that like the machine makers, where there may be bottlenecks, and but not necessarily from the end-to-end downstream processes. If there's another question on what are your bottlenecks in the manufacturing flow, that's different, and I can answer that too.
Okay, good. What about you, Bill?
I'll try to be really brief. I think just from a volume perspective, to Melissa's point, the printers output the most volume. While I wouldn't call it a bottleneck, it's just something that you have to adjust for, right? There's so much more data coming out of the printers than the other steps in the process. The other thing I would touch on is suppliers, not necessarily machine suppliers, but if you're working with an additive supplier, making sure that that supplier is capable of giving back the data that we require to do that analysis. And so I'd say just from those 2 different perspectives, those are some of the things we think about when we talk about, you know, digital thread and data accessibility.
If I can just add a little plug there, and that's why on that last statement, Bill, we use that secure print so that when we send a print to a supplier, it's streaming back into our archival library. So we have addressed that part.
Yeah, exactly.
Yeah.
Okay, good. Well, thank you, Mike, for appreciating the answers. I'm just reading your comments now. And then question number 13 from Maximilian. Where would you like to see or wire the processes in the future, and especially in aluminium application? Well, I like those questions about wire DD. I think that we will have a follow-up, conversation around that. But who would like to go ahead?
You know, I mean, we're using wire-based DED. We're not using it with aluminum yet, and where would we like to see the processes in the future go? I mean, wherever these parts I'm having a weird echo on myself. Sorry. You know, basically wherever, you know, we can find application, right? If there are applications for aircraft for large aluminum wire, you know, made with wire DED, we'll definitely go there, right? So finding the application, it has to be driven by an application, not just because we think it's, you know, really neat to study, right?
Yeah, agree. Okay. We're not focused with respect to DED. We're not focused on aluminum yet either. So yeah, we have other alloys that we're targeting for DED application at this time.
All right. Well, thanks, Marina, for your comment. Well, we are reaching the end of our conversations. Just in 1 minute, would you like to say, well, a short concluding thoughts for the audience about this topic? I know there were so many questions that needed to be answered, but just in case, just in 1 minute, like a few concluding thoughts.
Oh, I'm sorry, Katie. I the last closing thoughts. Is that what you asked? Oh, okay.
Yes.
Well, thank you for listening to us, and I think you got the same responses from both Bill and I. You know, we work in the same industry. That everything about additive is about you know, repeatable, stable process, and you know, ensuring that there's value to making that part. I mean, I think those are the two key ways, that your part is adding value to the end product. You're not just doing it for the sake of doing it, and that for production, we really need stable, repeatable process.
All right. Thanks, Melissa. Bill?
Yeah, first of all, thank you to the participants. And again, thank you again to 3D Adept for setting this up. It's been a pleasure to be here with all of you today.
Pleasure.
In conclusion, I would say, yeah, you know, safety, quality, paramount for Collins. And so while we're really excited about the future of additive and we're investing in that, it will always come back to those two fundamentals, safety and quality. And so there's a lot of work to be done. We're making great progress, not only at Collins Aerospace, but across the industry with our great partner at Boeing and with others. And so I look forward to meeting more of you in some of these sessions, but also, more importantly, perhaps working with some of you on a firsthand basis as we continue to mature the additive industry. So thank you again, Ketty. Thank you, Melissa. It's been a great pleasure spending time with you guys today.
It's a pleasure. It was really a great conversation. I'm really happy to kick off this, you know, season 4 of Additive Talks with the two of you. There was one question that we didn't have the time to answer from Martin Mahon. Martin, don't worry. I will send these questions to the two speakers and ensure a proper follow-up during the upcoming days, and we'll have the answer published on our online media with the recording of this panel. Thank you very much for listening to us. Please stay tuned for the next panel that will be announced soon. Stay safe and, well, stay tuned wherever you are in the world. Thanks a lot. I think that the session will close now. Thanks. Bye. Have a nice day.